you're going to have like not much of an idea about whether, when you're done or not. It was a question Kevin asked, right? It's like you can definitely, you'll make some reactions in some species with some numbers, and probably if you run it, it will not go exactly through whatever experimental data you have access to, and then you have to figure out what to do. So I'm going to talk about some thoughts about what to do about this process. So I think the most important thing actually is to start to have some expectation of what you're doing. So what do you expect is really happening in the system you're trying to model before you start to build the model? You need to think of, what do you expect the result to be? What are some species you expect in the model? What are some products you expect to come out of the reactions? What intermediates do you expect to see in the model? And maybe some rough time scale. Do you expect this to be like microseconds? Do you expect this to be years? And what observables are you really trying to predict with this model? Because the model's going to predict a zillion things, but you obviously don't care about all of the species and stuff. And also what kind of accuracy you're going to need in the end, because that's going to influence a lot about how much effort you put into trying to get all the parameters better and build the model bigger. The purpose of the model is to try to make a function that predicts the rates of change of all the species. That's what a chemical model is. And that was going to fit into some kind of reactor model after you're done. So there's this chemical term, and then there's some like diffusion terms and convection terms to get the overall rate of change of species in your system. And the chemical term is the rate expressions that you know, K's times rate coefficients, and then with back reaction with the equilibrium constant. And so in order to represent omega, the rate of change of the species, we store this usually in a chem-chem type format, where you have the reactions right now. It shows the stoichiometry, and then the rate coefficients expressions for each reaction, and some thermo that you need to calculate the equilibrium constants. And currently in RMG, we don't worry about the activity coefficients. We just sum all v1. Now, why is our prediction of omega wrong? There's like two main reasons why it's wrong. So one is that the numbers we have, the K's and the K equilibriums, are incorrect. And so we can, if we think that that's the main problem, we can work to get better numbers for the K's and K equilibria. And one thing that you can do is you can use arcane and arc and run quantum calculations and get good numbers for the thermo, for example. And it's like a relatively straightforward thing you can do. You decide this equilibrium constant matters for you, for your model. You can make it a better number by running some supercomputer time on it to solve the quantum chemistry better and get a better expression. Also, sometimes you can just look it up in the literature and get a good number, because typically what RMG is going to do, unless you tell it otherwise, it's going to estimate everything. And it's going to have estimates, but the estimates can be off by a considerable amount from the truth. So a lot of times you can just look up a number and be way more accurate, and then if you do a real accuracy quantum calculation, it might even be more accurate still. If you're really good, you can go down the hall and persuade Micah or Jim to run the quantum laser experiment and measure the rate coefficient for you directly. It's also possible. The other reason why the models are wrong is we don't have the right reactions in the models. So we have a thing called mechanism of truncation error, that we've cut off the reaction system somewhere. And we're not worried about every side reaction that might possibly be happening in our system. And what we're implicitly assuming is all the missing reactions have K's equal to 0. But K equals 0 is a lot different than the real K values. So this is a pretty drastic assumption for those rate coefficients. So we have a lot of K's, we're trying to get them really good, within a factor of 3 if we work really hard. And then we have these other K's where we're like off by 10 orders of magnitude because we assumed it was 0 when it's 10 to the 10th or something. If we think that this is the reason our models are incorrect, the solution is to make the model bigger by adding in the extra reactions. And that's really what RMG's job is to do mostly. RMG is trying to add more reactions in the systems. And there's two kind of cases. One case is that RMG knows about the type of reaction and just didn't put it in the model yet. And if you just tighten the tolerances of RMG and you force it to run longer, in principle, you should be able to solve that problem. Another case is that RMG doesn't even know that this kind of reaction is even possible in the world, and you can run RMG forever, and you never get this reaction. And so the solution there is you have to add a new family, or you have to add a library reaction for the missing reaction yourself. This general topic, I wrote a book chapter all about it. You might want to read. It's a lot of analysis and different issues about this. here's a math version of those errors. So there's one error is you take our model and our rate coefficients k and the equilibrium constants k are not the true values. And so if I put the true values in, the rate of change of the species that I compute will be different. And so that's the difference. Where I take my current model, I just changed all the numbers, or I'm looking at the deviations between the numbers I'm using and the real true numbers. And the magnitude of that is the parameter error. There's another one that I'm not using the full model, so I don't include all the reactions in the universe, but I only have some small set represented by this matrix Z, which is like has some ones and then lots of zeros, which are all the reactions I've neglected. And if I put them all back in, I get this difference. And so these are the two different types of errors I have. So if I want to reduce them both, I have to do two different things. I have to run RMG more to get more reactions, and I have to do quantum calculations more to get the numbers more accurate. And because of the way RMG works, you have to do this iteratively, because RMG's selection of what species to put in the model and what reactions belong in the model depends on its estimates of the Ks. So you have to have, you build a model, you improve some of the important Ks, that's going to change the estimation of what the concentrations are, which is going to change which reactions are important, and which are going to change which side reactions are important, and then RMG will decide which side reaction to add based on your updated estimation of the concentrations. And then when you run RMG again and do sensitivity analysis, you'll often find that some different reactions are sensitive. So in the example that Lon showed early in the beginning, it's like we had a really great model for pyrolysis. It worked great at the conditions at 1,000 Kelvin, but it was wrong at 1,500 Kelvin because during that change in conditions was enough to change what was important. Same thing can happen if you change a sensitive rate coefficient a lot. It can change a lot about what happens in the system, and so you have to rerun the model. Yeah?
Is there any disadvantages for having a really large RMG model? Like, other than the computation time, you might have...
Yeah, so I think there's I think in general there's no disadvantage. Sometimes when you make it really large, RMG might put some complete nonsense in, and that might screw it up. But more commonly, you make it large, you'll add in a few more important reactions and a whole lot of other ones that aren't important. And it just makes it more confusing for you, but it doesn't make it any worse. And the fact that you added a few more important ones might significantly improve the accuracy. So in general, larger is better. And our main trouble is not usually that we're unhappy because they're too large. It's more that we just have trouble making RMG make them too large because it just takes a lot of CPU time to build a model. It's not actually solving it, typically. We are getting within like an order of magnitude where you might start worrying about the solving time too, but that's not currently not the issue. Usually it's the RMG process of building the model is too slow. So we can't even get up to the point where we have to worry about the CPU time. And then another important thing is that you'll see the sensitive reactions and you'll do quantum calculation in your sensitive reactions, but what you really should do is update the estimates so that all the similar reactions will have better numbers. Currently this is a little bit difficult to do, but we've been working on trying to make this better, and this is like an important step to, because otherwise what happens, like you fix a certain beta scission reaction and that rate will be better, but then there'll be the analogous beta scission reaction where there's a methyl group on the side, and RMG will still use the same lousy estimate for that one. And it'll be wrong until somebody notices it's different. But actually, we should just update the estimate because it should be, the methyl group shouldn't make that much difference. So that's another kind of thing we should do here. This is more detail of how RMG is actually working, where it's based on the current estimates, it selects a species, and then this is how it decides which reactions to add, which species to add, which reactions to add. And then we would typically do this two-step thing where we also have to refine all the numbers. And I'd say this thing where you improve the estimates is a way to have a cumulative continuous improvement where everybody's work is helping everybody else out because your better numbers are improving the estimates that everybody else is using for their systems too. All right. So you succeeded to build a model. Now you have a model, and the very important thing is to actually go back and remember what your expectations were from step 0 and compare to what you see and see, does this model satisfy your expectations or not? And typically it will satisfy some of them and not all of them. And I highly recommend you actually write down the ones that it didn't satisfy that are annoying you. What is wrong with my stupid model? It doesn't satisfy my expectation about X, Y, and Z. And then those are like our to-do list is to try to fix that, right? We have to figure out why it didn't satisfy those expectations and what can we do to make the model better. A very helpful thing to do is to look at the major species in the model, the current model, and see if any of the species that show up there look completely crazy to you. Your eye is actually a really good way of detecting crazy stuff. And so you can go through and you might have 300 species, but 3 of them are completely nutso, and you'll see it. And then one of the things you can do is go, and very commonly what happens is that the nutso species, something went wrong in the estimation routine. We misestimated the thermo by a lot. And so if you go back and look and see what they're estimated, the numbers look crazy. We just run a quantum calculation with ARC. We just showed how to do it, and run it and get with Arcane and get the thermo number and put it in, and you rerun it, and that species will disappear because if the thermo is high enough, it'll be out of there. And these calculations nowadays are not expensive, and it's not really hard at all to do this. I highly recommend it. But keep in mind, the whole thing is going to be iterative. It's extremely unlikely that your initial model is going to be satisfactory to you. And so what you're going to end up doing is you're going to go through titling tolerances, considering different reaction conditions, refining some thermos or rate constants with quantum calculations, and doing this over and over again. And this is going to take you this is several weeks of your life. You're going to be tied up into doing this. And you have to just accept it. That's what you want. If you're going to make a model you want, this is what it takes to do it. So it's not going to be a rush. Don't try to just jump to the solution. Take your time. Think of systematically. Okay, I got to fix this and this and this about this model. You can look at it, and when you look inside it, it will not be hard for you to find a few things that are wrong with your model. Yeah.
General question for maybe Max and Mata. So when you restart the model, can we use our previous mechanism as a safe mechanism, like a restart point, or if you start from the zero again?
You're asking, is it better? Can you do that, or is it better?
Can you do that?
Good
Is it
to
better?
do that?
Yeah.
I mean, you can do that. I mean, you can start from it. And then also, some of it depends on how much you've changed in the parameters. Because of course, the old model was built with the old parameters, and so you can have a lot of cases where RMG tends to, and I'm going to talk a little bit about this tomorrow, is that RMG tends to be biased towards the pathways it's already found. And so in some cases, there's some cases where you may have potential to miss chemistry as a result of the fact that you just gave it all of these pathways. That isn't always a huge problem, and you can get away with that, with sort of restarting that way. It's a little bit it can be sometimes. I mean, it's what it says is that it's better to start from the beginning. You can start with a big seed mechanism and see what it goes. And if you haven't changed much, it's probably not that huge of a problem.
I'd say also that if you know that you're not going to accept a model unless it has species X, Y, and Z, then you want species X, Y, and Z to be in the model from the beginning, because you know you're not going to accept it anyway, right? So if you could put them in a seed or in as zero concentration species input file or something, anything you can do to try to help those species show up soon, and particularly if you know that they affect the chemistry a lot, your model's not going to be doing anything sensible until it gets those species in. So for example, you're doing a combustion problem, if you don't have OH in there, there's no reason to be doing it, because nothing burns without OH. And so you might as well put OH in from iteration number 1. You have some OH in there, and then you've got some H abstraction reactions and things that will start going. When you get the models bigger and bigger, it gets more and more unclear, because what the model was generated the last time will typically be a mix of some species that are really good and should be in the model, and some other ones that the foolish model foolishly put in. And whether you want to carry those over or not is more doubtful. But if you have species you know are really going to be there, you might as well tell it, because otherwise the poor computer's got to figure it out again each time.
Another thing is that now you can actually tell it. You can restart the mechanism and add new species to it. And so what you might do is that if it sort of, I guess it depends on your development timescale. You probably, when you want to do your final one, you probably want to start over and do from the beginning. But it might not be reasonable if you're not making that many changes. If you suppose you run your first model, and suppose it's a really long one, it takes a week to run. for a really large species, then it might be very reasonable to just find the species that are missing that you think you want to be there, put those in there, and then run it out of it, and then look at them all sort of as a whole. And then later on, once you've sort of gotten more of this correct, you can go back and run it from the beginning.
All right, what else? When you start, your model's going to be really bad, so it's often very reasonable to use extremely loose tolerances and just get it done. Because then you're going to do sensitivity analysis and find out that a lot of your sensitive parameters are nonsense numbers, and you can fix them. As you run and you get your parameters, the important parameters get better and better, and you start to believe them, then you should tighten your tolerances, because now you'll be more limited by mechanism truncation error. Is going to be a problem, not the parameter error. But initially, a lot of times, the parameter error is going to be way off because you don't have the thermo, say, for the key species, right? So it's, again, it's a very iterative thing, and you have to keep switching. Be working on quantum chemistry, and then be working on trying to get RMG to grow more. And a lot of times, right from the beginning, if you know that certain species are important, you can just like spawn quantum jobs for all those species right off the bat, because you're going to need good thermo for all the important species by the end anyway. So you might as well just calculate. All right, so again, if you knew that you needed 72 species, put the 72 species in. And you can do it, you don't have to do the very first one, you can put them in after you have a model that's semi-good. But if you care about this pollutant, you need pathways that lead to that pollutant, or else your model's not of any use to you. All right, and the rate-based algorithm is generally better as the rate estimates improve, which means as the concentrations improve. So if your current model is missing a key reactive intermediate, or if any of the sensitive rate coefficients are way, way off, or thermo is way, way off, or if some of even the rough numbers that aren't that important, if they're wildly off by factors of a million, in any of these cases, your concentration estimates can be bad, in which case the algorithm will be completely going down the wrong tree. It's not going to know what's important. So you're going to have to get all these things fixed. But then if you do have all these things fixed, the RMG algorithm is actually pretty good at selectively adding the next byproduct. And because it's like, that's the way the algorithm's set up, is if you have roughly the concentrations are right, and it's just adding a little bit of minor perturbations at a time, it should be okay. But at the beginning, you really don't know if the model's have any reality at all. All right. So again, make sure you have expectations. Pay attention to the convergence. If RMG says it's not converged, it's not converged. It's not kidding you. That means it's still finding reactions that have rates that are higher than whatever you set your tolerance at. But a lot of people get bored and you get fed up and you wait and you don't want to get it done. That's fine. You want to see your mechanism so far, it's fine. But just realize RMG's telling you there's a lot more reactions out there that you haven't bothered to put in yet. And at some point before you publish it, probably going to have to put them in. So just be aware. And then crazy species often are a big problem, so just look for those. And then we have the file that has collision limit violators. Open the file. See if you have reactions that are crazy. Often that'll be the problem. And there's also sometimes make the solver have trouble because they make it too stiff. A lot of trouble because of that. Okay, so when you start to get a model you think is semi-good, look at the selectivities. Is it making the major products you expect? Are they anywhere reasonable? If you have any experimental data about what some major products are, it's a great time to check. Usually RMG gets the selectivities better than it gets conversions. So work on the selectivities first. That means you're getting the main channels right. Don't worry about the conversion. The time scale usually will be wrong. And if you're doing sensitivity analysis, be sure you do sensitivity to thermo. If you're using ChemKin that doesn't have thermo, and you might be tempted not to do it, do it. We have tools that can do sensitivity to thermo. They definitely do it. Often the thermo sensitivities are bigger than the rate sensitivities. Also, the thermo we can do something about because we can calculate them pretty well. And if you find you're sensitive to something, you can run some fancy-dancy quantum chemistry thing and get some really great number. And so do it. Also, if somebody published some stupid BA3 lit number, don't just type it in your library file, because maybe you're condemning yourself to have a terrible number for that molecule for all time. So make sure that the numbers are right. Even these really good methods, the errors are still order of a kcal, which is pretty significant when you consider the temperature. So the energies come in like an equilibrium constants as the error in the energy divided by RT. So if this is a kcal, that means even up to 500 Kelvin, this is already a factor of 3 uncertainty in the equilibrium constants. So that means you should not expect that your model is going to predict all the numbers within factors of 3. So you have to be very lucky for that to work out. because all your rate constants and all your equilibrium constants mostly will have errors of orders of factor 3 in the best case. If you're a lower temperature, like if poor Oscar doing the Pfizer project, trying to room temperature, it's like you have errors that are factors of 10 everywhere. Every number would have an error factor of 10. And another common mistake I see a lot is students get very upset because their model is not predicting species 17 that was measured by somebody once, and it's not predicting it right, and then they'll do anything they can to make the model get that number right. Okay? The goal of this process is not to make a model that predicts that one number. You try to make a model that's like correct, it's like the truth, and you can easily alter some constant, some parameter in your model and force it to predict anything. But again, it's like the elephant's tail problem. It's like just because you can make the elephant's tail wiggle as you vary your parameter doesn't mean you really understand how elephants work, right? And so, so often you'll find is this expression, closer to the truth, further from the data. You'll find a model in the literature, it matches some data set, then you build the RMG model, it won't match it, and you say, well, what's going on? They had some stupid model, and I use my fake fancy RMG model, and it's not as good as the model they had before, but it's that you were putting more stuff in that they forgot, and they tweak the parameters to force it to match that one data point. It doesn't mean that model is any good, the one in the literature. And you're not judged by the fact that you can go through that one point. You can obviously make a model that goes through one point. It's not the point of this exercise. But I see this a lot. It's like people are upset because their model's not getting through this one point. But if you just look back at this, of course, you're off by a kcal. There's no way you're going to go through every point. I mean, you should expect at least factor 3 errors everywhere. So if you have better than factor 3, it's like you probably cheated. Yeah. So you're going to be tempted to tweak the parameters and force them to agree with the experiment. I highly don't recommend this. However, I know some of you will do it anyway, from my experience with students. If you do it, be careful. Okay? Just be aware, you have too many parameters in these models. You're not going to be able to figure out which parameter to tweak to make it match. And if you do decide, okay, I can tweak this one parameter and force it to agree, you definitely have to publish that and say, when I got the model, I predicted it was off by factor 7, but I can just adjust this one rate constant, it was one thermo number by a couple kcals, and all of a sudden everything's great. Okay, that's fine to say it. If you say it straight like that, then everybody knows, okay, this is a model where I can believe all the parameters except that one was like fudged to make it agree. But the problem I have with this is it makes people start to believe that RMG is like predicting things to the super accuracy, when actually it did not. It's just that your tweak made it match it. So anyway, if you're going to use, if you're embarrassed to tell people that how you went and tweaked, parameter 17, then don't do it. Okay, your embarrassment is your conscience telling you not to do it. And it's also, you'll do sensitivity analysis. It's very important to combine it with uncertainty analysis because the variance in the uncertainties is really huge. There's some parameters we really know them to a lot of decimal places, and other ones we have really no idea. And so you have to consider both factors when you're considering this. I think that's all I got. All right. Any questions? Or?